Hello everyone and welcome to Course Bridge. In our last tutorial on Fourier series, we looked at what odd and even functions are, their Fourier series expansion, and we also saw how to find the Fourier series of functions that are defined in subranges. In today's tutorial, we will solve a question to illustrate what we've learned so far under Fourier series. The question says, sketch the graph of function f of t below and find its Fourier series. So as you can see, f of t is a piecewise function, and from 0 to pi, we have t sine t, and from minus pi to 0, we have minus t sine t. So brace up, guys. Let's get started. So let's start with the graph. So before trying to draw the graph of t sine t, I believe you all know by now that for sine t, forgive my line if it's not straight, we would have a curve like this, where this is 1 and this pi over 2, pi, 3 pi over 2, and 2 pi, and so on like that. And here we have minus 1. Here we have minus pi over 2. We have minus pi. Yeah, and it goes on the way. But now we've been asked to sketch the graph of t sine t. Now, because we're having t multiplying sine t, it means that the magnitude of the curve would depend on the value of t. So as t is increasing, the curve is increasing, but as t is decreasing, the curve is also decreasing. So let's see what a typical sketch will look like. So we have this. So as the value of t increases, our curve also increases. Then you get to a point where the value or the amplitude of our curve is same as t. We'll get that point together now. This goes by, I can come and do the same thing here for minus t sine t. Now what is this point? We know that if our t equals to pi over 2, we would have pi over 2 sine pi over 2. And since sine pi over 2 is 1, which happens to be the highest value for our sine, it means the magnitude here is pi over 2. And similarly, the magnitude here is minus pi over 2. So we have from 0 to pi, and we have minus pi. So that solves the question for just the graph sketch. Now let's move on to finding the Fourier series. And also for the graph, you can test the accuracy of the graph by plotting it probably with an online tool, or by inserting certain values to see the coordinates and plot out the curves itself. But as you can see, let me show you. Okay, this is Wolfram, and you can see the curve that was being plotted by Wolfram. Very similar to what we had. So that's just to ensure that we are accurate. So I'm going to clean the question off and just write it somewhere. So let's clean this off. So like I said in the first tutorial, whenever we have to find Fourier series, we basically need to find out three terms, which are a naught, an, and bn. And before I move on, from the sketch, is our function odd or even? As you can see from the sketch that the function is symmetric about the x-axis. And even with that, we all know that sine is an even function. Did I say even? I meant odd. So it means that that function that we just plotted the graph for is an odd function. And in the last tutorial on Fourier series, I made it clear that for an odd function, we don't define a naught because we proved that it's 0. An also 0, but bn is equal to 1 over the period over 2, going from, let us say, a to b of f of x sine nx dx. Now this is usually from minus pi to pi, and e is from minus pi to pi is same as us having double, which is times 2, going from 0 to pi. Now I explained all this in details in the last tutorial, which is our bn. So now let's just go on to find the bn for this function. So for this function, what's our period? Our period is 2 pi. So it means our bn is equal to 1 over pi, which is 2 pi over 2, integrating from 0 to pi, t sine t, sine n of t, and also integrating from minus pi to 0, minus t sine t, sine n t dt, and dt. So we can see that these two functions are actually the same thing, except for the minus here. So quickly, together, let us find the integral of t sine t sine nt. To do this, we can use this trigonometric expansion. That sine a sine b is equal to 1 over 2 cos a minus b minus cos a plus b. That means what we have here is equal to 1 over 2 integral of t cos t minus nt. Put this here, plus integral of t, this will be minus integral of t cos t plus nt. So to make our work easier, let's find the integral of either of these. So let's find the integral of t cos t minus nt. I know what, let me do that somewhere. So we have integral of t cos t minus nt. We can integrate by part here. This is our u, this is our dv. Remember I said for by part we have uv minus integral of v du. So let's go, we're going to have t, our v is the integral of dv, which is sine t minus nt all over 1 minus n. How did I get 1 minus n? The differential of t minus nt. Then minus integral of v, what's our v again? Sine t minus nt 1 minus n times du. What is the differential of t? That's 1. So here we have t minus nt so we have integral of sine t minus nt over 1 minus n is equal to minus cos t minus nt over 1 minus n multiplying 1 minus n. So basically this will give us t sine t minus nt plus cos t minus nt all over 1 minus n all square. So if what we have here is the integral of t, let me go back to the other board and check what we just saw again. T cos t minus nt t cos t minus nt, it means that similarly the integral of t cos t plus nt will be equal to t sine, here we have minus, they're going to have plus, t plus nt all over 1 minus n here, 1 plus n, then plus t plus nt over 1 plus n all square. So putting them together, we have 1 over 2, or no, we have 1 over 2 pi based on the 1 over pi that we have here. So we have 1 over 2 pi. Or even before we do this, let's come back here, put our limit, just to make our work faster. So we have 0 to pi here, and we have minus pi to 0 here. So let's do for each of them. I can just remove this. So integral of 0 to pi t sine t sine nt is equal to 0 to pi of t sine t minus nt over 1 minus n plus t plus cos t minus nt over 1 minus n all square minus t sine t plus nt over 1 plus n. Then we have minus again cos t plus nt over 1 plus n square. Now, in case you are wondering where minus came from, let me go back and reference that so we are all on the same page. So remember, we found this and we found this. Now we're both having plus, but because we have a minus here, expanding this guy will leave all the term as negative. So I hope that was clear. So now let's plug in our limit here. Now, to avoid wasting our time, we know that if we plug in 0 or pi, this goes to 0. This also goes to 0. So we are left with this. We are left with cos pi minus n pi 1 minus n squared. Then we have minus cos pi plus n pi, 1 plus n all squared. Then we have minus cos 0 minus n times 0 all over 1 minus n squared. Now plus, because if you have minus here, this becomes minus and this becomes plus. Plus cos 0 plus n times 0, 1 plus. And in case you're wondering why I cancelled out sine and sine again, plug in the value of pi for t here. Sine pi is 0, sine 2 pi is 0, sine 3 pi is 0. Only sine pi over 2 will give us a magnitude of 1. And if I plug in 0 for the value of t, sine 0 is always 0. So from here, what can we do? So we have cos n minus pi, n minus 1, 0, no, let me go back. Let's do it again. So we have pi factorized outside, and we have 1 minus n instead. Good. Over 1 minus n all squared minus cos pi into 1 plus n over 1 plus n squared minus, oh, this is 0, 0, because 0 is 1. So we're left with this plus 1 over 1 plus s n all squared. So this is for, let's go back here. So what we have just solved now is the integral of t sine nt from 0 to pi. So let's put that down. We have okay, let me put that down here. We have cos pi n minus 1 over 1 minus n all squared minus cos pi of n plus 1. Or instead of us putting n plus 1 and n minus 1, recall that I explained in the first tutorial that if you have cos n pi, same thing as minus 1 raised power n, because the value alternates between negative and positive 1 for different values of n. So if n is 1, cos pi is minus 1. If n is 2, cos 2 pi is 1, which is same thing as always doing minus 1 raised power 2 and getting 1. So that means if cos n pi is equal to, if cos n pi equals minus 1 raised power n, it means that if we have cos probably n plus 1 pi, it should also give us minus 1 raised to power n plus 1. So I'm going to replace all this. What did I just do? Okay. So our cos pi 1 minus n over 1 minus n squared becomes minus 1 raised to power 1 minus n over 1 minus n squared. Let's go back. Our cos pi into 1 plus n over 1 plus n squared now becomes minus 1 plus n over 1 plus n squared. And then we are left with this minus 1 over 1 minus n squared. I think the last one plus 1 over 1 plus n squared. So now let's go to the next part, which is same integration, but now from minus pi to 0. Now if you're following, the integral of t sine t sine n t dt, it gave us t sine t minus nt over 1 minus n plus cos t minus nt over 1 minus n all square minus t sine t plus nt over 1 plus n minus cos t plus nt over 1 plus n all square. Now let's plug in the limit here, which is minus pi to 0. So similarly, our sign expressions goes away. We are left with this and this. Now let's plug in 0. We'll have cos 0 minus n 0, which is still cos 0, and which is 1, because 0 is 1. So we have 1 over 1 minus n all square minus, we have 1 here also, 1 over 1 plus n all square. And let's plug in minus pi. We have cos minus pi plus n pi, because our minus here will cancel out minus here. 1 minus n square. Then we have minus pi minus n pi 1 plus n square. So this will lead us to 1 over 1 minus n all square minus 1 over 1 plus n all square. Now factorizing here, we should have n minus 1 pi. So this gives us plus minus 1 raised to the power n minus 1. But let's go back and check this. Here we have 1 minus n. Here we have n minus 1. Now the question is this: is there a difference? Well, we'll find out. So yes, they are the same thing, because let's try out a simple value. If you have minus 1, say 3 minus 1, you get minus 1 raised to the power 2, which is 1. But now if I change this to minus 3 plus 1, you get 1 raised to the power minus 1, which is just 1 over 1. So we will see why I'm saying all this very soon. Okay, so we have over 1 minus n all square. Then we have factorizing here, we have minus pi into 1 plus n. But because cos is an even function, cos of minus pi 1 plus n is same thing as cos of pi 1 plus n. So we can write this as minus 1 raised to the power 1 plus n over 1 plus n all square. This should be a square, my bad. So we have this. Now let's go back to our previous screen. Now we have just found the integral of this, and we have kept our minus pi to 0, but there's still a negative sign here, which means that before adding this here, every of the term should be multiplied by a negative value. So let's go. The first thing here is 1 over 1 minus n squared. So we have minus 1 over 1 minus n, should be brackets, all square. Next thing we have here is minus 1 over 1 plus n squared. which becomes plus 1 over 1 plus n squared. 1 plus n squared. The next thing we have here is minus 1 raised to power n minus 1 over 1 minus n all raised to power 2. So this becomes minus now. So we have minus 1 n minus 1 1 minus n all square. In the last term, we've got minus 1 raised to power 1 plus n over 1 plus n squared, and negative here becomes plus now. So we have plus negative 1 plus n. Let's see this again. Over 1 plus n all square. So let's go back and check what we did again. Let's check our signs properly. Okay, I found a mistake. Now when we inserted 0, we had this, we have this. Now before inserting minus pi, we should have a negative. So we should have a negative multiply this to give us. So we have this. And if you're integrating f of x from a to b, so whatever I get as the integral, let's just call it f of x again. It should be f of b minus f of a. So I forgot to multiply this by a negative. My bad. So yeah, we have negative here, and here we have plus. Means we also have negative and plus. Negative plus. One is to be very, very careful with the signs. So let's go back. So it means negative now becomes plus here, and the positive here now becomes a negative. Okay, so I can rub this off. How many minutes have we used? Okay. So now simplifying this, our bn is equal to 1 over 2 pi. Now, like I explained earlier, minus 1 raised to power 1 minus n over 1 minus n squared and minus 1 raised to power n minus 1 over 1 minus n squared are the same. So we have 2 into minus 1 raised to power 1 minus n over 1 minus n squared. Now we have a negative, and we have the same term here. So you have minus 2 minus 1 raised to power 1 plus n over 1 plus n all square. And what else? Okay, we have a negative here. We have minus 2 over 1 minus n all square. And finally, we have a positive for these two terms, which are equal. We have plus 2 over 1 plus n all square. So we can still simplify further. We can factor out 2. Let's factor out 2. So our bn now equal to 2 over 2 pi minus 1 minus n over 1 minus n square minus 1 plus n over 1 plus n whole square minus 2 1 minus n whole square minus 2 again, sorry, and minus 1 instead. Then plus 1 plus n all square. So I hope you're on the same page, guys. So our two cancels are 2 here. So we're basically left with 1 over pi as our final answer for bn. But remember, this is not where we stop. For our Fourier series expansion, we have a naught plus summation as n goes from 1 to infinity of an cos n of x, and summation as n goes from 1 to infinity of bn sine n of x. Our a0 is 0 here, fine. An is 0 here, fine, but we still need to express our bn in this form. Now, taking the entire bn and plugging it here will be very wrong. So what can we do? Let's find the values of bn for n equal to 1, n equal to 3, for 2, for 3, and 4. Let's see if we find the pattern. So when n equal to 1, what do we have? Our b of 1 will be 1 over pi. So let's work through this together. We have 1, making this 1 minus 1, making this 0, making this 1. And also, when n is 0, when n is 1 rather, we have 1 minus 1, which is a problem because we'll get 0. Now 1 over 0 is indefinite, so we can't even proceed from here. So one approach to take in a situation like this is to go back to your original integral and find your b1 directly. This is what I'm trying to say. So our original integral, we had 1 over pi going from 0 to pi of t sine n t dt minus going from 0 minus pi to 0 minus t sine n dt. So to find our b1 here, let's plug in 1 for our n here. So it means we are looking for the integral of t sine square t. To make our work easier, let's find that one separately. And I hope you know how I got sine square t. Let me go back. Basically going to have sine t, sine 1t, which is 2 sine t, and that's how I get sine square t. So now how do we integrate this? We can use by part again. This is our u, this is our dv. And remember, this is uv minus integral v du. So we have t, where v is the integral of dv. And now to integrate sine square, one trick I use is to change sine square. There are lots of trigonometric functions that we should know. This will help us in solving calculus. So we have sine square t is equal to 1 minus cos 2t all over 2. So let's go back. So we have integral of t 1 minus cos 2t all over 2, which means our integral is now integral of t over 2 minus integral of t cos t over 2. Integrating t over 2 is straightforward. We get t squared over 4. Now integrating t cos t over 2, let's do that somewhere here. Again, we use by parts, and t is our u, so we have our t. Cos t, let's factor out our 2, so we have 1 over 2. And our cos t is our dv. Integrating cos t, we get sine t. Then minus integral v du, where v is sine t and where du is 1. So this gives us t sine t. Integral of sine t is minus cos t. So this gives us t sine t plus cos t. But remember, oh, another mistake. I think I found that out early. So this should be cos 2t. So let's go over this again. So we have where we say 1/2 outside. So we have t. Integrating cos 2t, we get sine 2t over 2 minus integral of sine 2t over 2 times differential of t, which is 1. So we have t sine 2t over 2. Now integrating sine 2t, we get minus cos 2t over 2, making the entire thing here minus cos 2t over 4. And when you expand, you have t sine 2t over 2 plus cos 2t over 4. Now bringing that back here and multiplying each of the term by a negative, we have t sine 2t. Hold on, let me grab my charger before this laptop goes off. Okay, I'm back. So we have t sine 2t over 2 minus cos 2t over 4. So let me write this clearly again. So what we are saying here now is that integral of t sine square t gives us t square over 4 minus t sine 2t over 2 minus cos 2t over, should be over 8, and this should be over 4. Why? We have 1/2 outside here. So we have this. Now we have to find what this is for the range 0 to pi, and find what this is for the range minus pi to 0. So let's start for 0 to pi. And of course, our sine t goes away. So now we have, for pi, we have pi square over 4 minus cos 2 pi, which is 1 over 8, minus 0 square over 4, just 0. Now we get plus, because negative here multiplies negative here. Plus 2 times 0, that's cos 0, which is 1 over 8. So for the range 0 to pi, integral of t sine square t equals pi square over 4. Now let's find this for minus pi to 0. So of course our sine 2t goes away. Now for 0, we have 0 square over 4, which is 0. Then we have minus cos 2 times 0, which is minus 1 over 8. So we have minus 1 over 8, then minus, putting t as minus pi and squaring it gives us pi square over 4. Then we get plus, putting t as minus pi, we get 1. So we have plus 1 over 8. So from here we have minus 1 over 8 plus 1 over 8 gives us 0. So we are left with minus pi square over 4. It means that for this expression here, we'll have 1 over pi. We have pi square over 4, which is this. And this we have minus pi square over 4. But there's still a negative sign here. So that gives us plus pi square over 4. So we are left with this. 1 over pi times pi square over 2. So our B1 finally is equal to pi over 2. So B1, after a long solving, we get pi over 2. So how about B2? Let's do that quickly. We have 1 over pi minus 1. When we plug 2 here, we have minus 1. We have minus 1 raised to power minus 1. Yeah. Okay, so I'll just do this quickly on my calculator and get my final answer. Okay, putting n as 2, our B2 gives us minus 16 over pi 3 squared, which is like saying minus 16 over 3 squared pi. You can write 9, that's still fine. I just like to keep the squares the way they have whenever I see them in Fourier series. Okay, let's find out B3. Plug in 3 as you head and get your value for B3. So doing that, you should get your B3 as 0. Let's get our B4. Put in your 4 as n. You get your B4 as minus 32 over 15 square pi. Now that we have values for B1, B2, B3, and B4, let's write the Fourier expression. So it means finally, our f of x, what's our B1 again? Pi over 2. That's pi over 2 sine 1x, which is sine x. Now for all the rest, you see that we have over pi, which means we can factor out 1 over pi. So we have plus 1 over pi. What's our B2? Minus 16 over 3 squared sine 2x. Our B3 is 0. And our B4 is, we have minus 32 over 15 squared sine 4x, and so on. So we've come to the end of today's tutorial. Please, if you are new to the channel, please like, subscribe, turn on your post notification to get more educative content on CourseBridge. And if you are just watching this video first, please check out the first 2 videos on Fourier series. It is very explanatory and it will make this video easier to understand. So catch you guys in the next one. Bye.